Okay, so number 18 is definitely the hardest problem probably in the book to do. And you want me to assign that problem to you so you can say that you actually did it and you experienced this problem. So there's a lot of little things going on in this cone problem that we need to talk about. So over here I've drawn you a little diagram of my cone. Again, don't hate on my skills. You can see that there is water leaking out of the cone as well as being added into the cone. So water's going in, water's coming out. We know from what is being said that the volume is actually getting bigger. The water level is rising. So that's going to be a key piece of information. We're also told some dimensional things about our cone. So starting with our EGF, we know that this involves volume, so we have our cone volume equation. And we are given two pieces of information, one very obvious, one not so obvious. The obvious piece is that dH dt is equal to 20. We're told that the rate at which the water is rising is 20 centimeters per minute. So let me even write that in. This is centimeters per minute. And that's an important piece of information because, again, it's positive, meaning that H is increasing. So if H is increasing, that tells me that the volume is increasing. And the second equation that I have to the right may not be the obvious one, is that dV dt is going to be found by taking some constant rate that is being pumped in and subtracting off the rate that is being leaked out. So dV dt is whatever the rate is going in, this water going in minus the water coming out. And we know that C is bigger than, the constant rate at which it's going in is faster than the constant rate at which it's going out because H is getting bigger. dH dt is positive. What we are trying to find, weird enough, is just the value of C, the rate at which this stuff is being pumped in, specifically when the height is equal to 2 meters. And that is another tricky piece of information. If you look at the problem, all of the information about this cone is given in metric, but it's not given in the same units. You're told that water is leaking out of the tank at 10,000 cubic centimeters per minute, and you're told that the dH dt is in centimeters per minute, and then you're told that the height is in meters. So one of the things we have to do to be able to do this problem is actually do a little conversion, that we have to go ahead and convert meters to centimeters, so our height is really 200 centimeters. If we don't do that, we'll be off by a factor in the end, a factor of 100. So, and that factor of 100 actually, I think, ends up getting squared or something like that, so it'll be off by even a bigger factor. So there is all of our given information. Now we need to worry about a related rates equation. As with the other ones that we did, we have dH dt, we don't have dR dt, so we need to get R in terms of H. So I would say that from the stuff we know about our cone, R over 2 is H over 6, so a proportion relating the radii to the heights, telling us that R is 1/3 H. So I can come back here and say that volume is pi over 3. And instead of R, we'll use 1/3 H squared, or H over 3 squared if you want to write it that way, times H. So volume is pi over 3 H squared over 9 times H, so H cubed over 9. Or how about we just go with pi H cubed over 27. So that is what I am going to be working with, pi H cubed over 27 as my volume equation. All right, I'm going to go on to the next page and continue on. All right, so getting the related rates equation, I'm going to have that dV dt, derivative of the left-hand side, is equal to pi over 27 times 3h squared dH dt. I can cancel this 3 and this 27, leave me with a 9. So dV dt is equal to pi over 9 h squared dH dt. I know that dH dt is 20. I know that h is 200. So dV dt is equal to pi over 9 times 200 squared times 20. That leaves me with dv dt. 200 squared times 20 times pi is 800,000 pi. That's a lot of pi divided by 9. Oh, it's not so much pi anymore. So 800,000 pi over 9, and this is cubic centimeters per minute. So that's dv dt. And normally we'd be happy with that answer, but unfortunately that's not what we're looking for. We are looking for c. What is the value of c? And we know that c is related to the amount of water being pumped in, but the rate of change of the volume is the water going in minus the water going out. So this dv dt that I have right here is actually c minus the 10,000 cubic centimeters that are coming out. This is c minus 10,000 is really 800,000 pi over 9. So again, let me just make sure that we all understand that. C minus 10,000 is the rate of change of volume. It's the water going in minus the water going out, so that's how the water is changing, and that has to equal what our dv dt was. The question is, what is C? Well, easy enough, just add 10,000 to both sides and you've got yourself the answer to this problem. So C is equal to 800,000 pi over 9 plus 10,000. All of that cubic centimeters per minute. That's the answer. So there was a unit conversion, there was a substitution in for the height, there was a weird little change of dv dt almost all the way through the problem to get the value of C. Ooh, sorry, excuse me. All right, so that is the dastardly number 18. If you worked your way through that on your own, congratulations. That is a very, very difficult problem to do. If you're watching this now and you're wondering what can I do over the weekend to become better at related rates, take the rest of the problems in the note packet and try to work them out. There's kind of a different take on some different Pythagorean theorem problems and rehashing some of the problems that we've already done before. So that would be my suggestion to you, and I'll have typed that probably in the directions to this video. All right. Well, thanks for watching, and I will see you on Tuesday. Have a great 3-day weekend, 4-day math weekend. Bye.